website and a LinkedIn. They're on LinkedIn too. I think Twitter, but it's not cool to be on Twitter now, so I won't say anything more about that. Okay, so first, uh, I want to talk a little bit about modeling catch information in well, states-based assessment models, but I guess in assessment models in general. And it's the type of catch information that I am faced with dealing with some of the East Coast or Canadian East Coast stock assessments. So essentially, we're given information about total fishery landings in weight, usually tonnage each year. And the catch numbers are estimated from the landings information and using somehow information on sampling of weights at age and the proportions at age in the stock. And I mean, I'll just give a kind of a simplistic equation for that, but in practice, this could be done in strata and so on. That may be more complicated than this, but basically, catch numbers are estimated from landings information and then sampling of the catch for age comps and body weights. So the landings then, the landings are what drives the catch numbers. And the landings come in the Canadian context, come from enforcement monitoring. And that can involve like dockside monitoring, log books, and other types of self-reporting, etc. And so it's coming from enforcement monitoring, and it's supposed to be a census, right? Like once there's in most directed fisheries, there's an allocated quota. Once the quota is reached, the fishery is supposed to stop. So the idea is that the catch numbers are like a census, but this is not how it works in reality. But unfortunately, I find the catch estimation, certainly in Canada and other places, ends up basically being like a black box to us. We really don't. The enforcement people don't like to advertise what they do or explain to to just explain how it works other than high level terms. So we don't really get very good information on the potential errors in the catch. Other than, we can get the errors in coming from the science sampling for weights and proportions and that. But, we're not really getting errors in the landings per se. And of course, we may get a discard information from onboard observers or from self-reporting via logbooks and that. So we usually have little information about the accuracy of landings. So I kind of think of these as uncertainty. We know they're uncertain, but we just often don't have very good information about how uncertain they are. And this is kind of similar to this kind of unknowns that became a kind of a popular thing back in the early 2000s by a U.S. government official. Anyway, but we may suspect or somehow know catches are underreported, or if there's some information on discards, or we may have some information on area or species misreporting, etc. And the uncertainty will change over the time series, most likely, because the factors or conditions that lead to error in the catches change over time. Like, for example, some early NAFO landings, so NAFO is the Northwest Atlantic Fisheries Organization, some of the early landings, I think it was routine that they actually negotiated amongst the countries what their landings were, which is a statistical challenge. Like, how do you model the uncertainty in the negotiated quantity? Optimal solutions may be case specific. So I've been using a kind of what would I call it, a naive uh, approach based on a censored likelihood or censored likelihoods, and I'll just explain quickly what that's about. So with the censored landings, what people call censored landings, we don't really give the assessment model particular values of the landings. Rather, we just tell this model that there are bounds on what the landings were, like a lower bound and an upper bound. And these bounds come from expert opinions. And then we use the bounds via censored likelihood to tell the model how good the landings are. And I just give some papers like Verena Trenkel and Tim Hammond first published this back in the 80s using the censored likelihood approach in terms of surplus production models. And then there's been some other papers. But an issue, of course, the bounds come from expert opinions, and different experts have different opinions. And for example, like I was just thinking about some work that this person, Danielle Duplessis, did in terms of redfish. Like, we were aware that we felt that the redfish catches in the late 80s, early 90s were underreported. So Dan did some interviews with fishermen and somehow come up with this red line, which they concluded was although the black line is the reported landings, the red line is the minimum likely catch from Canada. So, I don't know what the redfish people did. This would have been redfish in what's called the Northern Gulf of St. Lawrence. I don't know what they did with this information in terms of the assessment, but just gives some sense that there can be substantial uncertainty in the values of the landings. I mean, just really large uncertainties. So just a little bit about the one slide or two slides on what the censored likelihood is. So if we only know a range of the values for possible landings, then so I let the BLBU indicate the lower and upper bounds each year on Y's year. We assume some type of log normal measurement here. Anyway, the censored likelihood is really just coming this way. So it's just like, well, this is the log likelihood. So it's the log of the probability that the landings were within the bounds. And I mean, this is just more specifically how you compute this. So, but this is the type of likelihood I would include in a stock assessment model if the data were actually bounds on landings. And so LY is the assessment model predicted landings, and sigma C is the kind of a user something we set that really defines how sharp the bounds are. And I'll give an example of this log likelihood term in the next slide. So it's that simple. And so here's one, like, I guess, this is a case when the bounds were like 20 kilotons to 30 kilotons. And I'm just showing what what we call the NLL, right? The negative likelihood. I'm just showing what that looks like for a range of true landings and different choices of these sigmas. So basically, in terms of estimating the model, like usually I pick this sigma is 2%, so that would be the red line. And so it's essentially the model is free to put landings anywhere between the bounds, but it doesn't like it when the model predicted landings go outside the bounds. But as this sigma L gets larger, the model wants to basically put the landings at basically a half the between midpoint between the lower and upper bounds. So illustration from the 2016 Northern Cod assessment. I looked around for some more recent information, but they don't really publish much in this assessment other than just the basic results, but they don't really give much details on fitting the assessment model and that. But I could find some details from the 2016 assessment. So here's an illustration. On the right-hand side, we see the total catch weight on a log scale. So the bounds are these gray lines. And then the model, they use some type of state-space assessment model. So the model predicted is the black line. So you can kind of see that the model is, has to stay within the bounds mostly. Sometimes you can go outside the bounds. Mostly you're within the bounds. And other than that, the model has, it's free to do what it wants with landings. And these points are, I think, what do they call lower observed? So the lower bound divided by the predicted. So usually the model is, I think it's a bit easier. As I recall, the lower bound is usually 10% greater than reported landings. And you can kind of see that here. It always, this is predicted landings divided by observed. Well, predicted total catch weight divided by observed total catch weight. So usually the smallest it can be is 10% greater than the observed total catch weights. And I think the upper bound, I'm not sure in this period, but in this period it was about 2. So the model could predict with very little penalty landings that were double the observed total catch weight. And in fact, in 1 year, it went even more than double. So that's the gist of it. That's what's going on there. So you're not fitting to specific values of landings. The model is just constrained to keep landings within these bounds. And you can make the bounds as wide as you want. And so the bounds get really wide, then essentially you end up with what we like to call a catch-free assessment. So that's it's doable, but the scale of the assessment becomes quite uncertain. And here's an example on one from an assessment on I've been working on recently. It's the Thorny Skate and NAFO divisions. Well, 3LNOP, yeah. So one thing we do with the bounds, because we're not certain what the bounds should be, so we'll do some scenarios. So the NAFO assessor for this stock is very suspicious of the landing sinks. They're highly inaccurate, especially in the early periods of the time series. They think there were all kinds of problems with area misreporting and actually reporting. And it could be overestimation too, because the suspicion was that the American place, which was a bycatch species, was being reported as thorny skate. That's one of their concerns. Anyway, so we set some 2 scenarios. One had kind of wide bounds for the landings in the early period, and I think it's plus minus 25% in a more recent period. And I think this scenario was plus minus 25% always. And there's some details about how these bounds are put together, which I don't think we had to get into now. But so this is showing, I guess, the model fit to the wide bound. So the vertical lines are just joining up the bounds each year. And then we had the model predicted, and the gray lines are actually the observed landings, but now they're not being fit in the model. We just showed them there to illustrate what's going on. And so then we do this, fit the model to both of the landings bound scenario? Because some people they get kind of negative about using assessment models with these uh, landings information, and so at least we're showing, so we do the two scenarios here, and in the end, I mean, yeah, some of the results change, but for both scenarios on catch uncertainty, the eventual status evaluations are almost identical. So I guess, in some sense, like in this sense, in terms of status evaluations, I think the results are insensitive to the uncertainty in the at least the historic landings. And that's the recent landings had the same bounds in these two scenarios. It's just the historic period that's changing. And this is different than just doing catch streams, right? Catch streams, you're trying to fit to each stream, but this is just saying, that there's a lot of uncertainty. And remember that the model predictions can be anything they want, essentially, within the bounds. And so the specific values then are coming from other information like surveys and that. So that would be the way I would be addressing uncertainty in the landings. And it's kind of naive because we're using this just flat likelihood, if you will, between the bounds, and the bounds are subjective. And I wish I wish we had better information on the landings and uncertainty in landings. And if we did, I certainly would try to use it, but at least for Canadian stocks, I find that that information is often lacking. Okay, so that's all I have to say. Uncertainty in landings. Most of my talk is going to be dealing with size and age comps. So that we're in a better situation there, in a way, because at least in Canada, science samples the catches to determine length and age comps. So at least conceptually, we should understand the sampling programs. However, it's complex sampling, highly stratified, like there could be regions and quarters and gear types. I mean, these we can consider these to be strata, and then multi-stage cluster sampling. And because it's highly stratified, then in practice there can be unsampled strata. And here's a problem for certainly assessments in the Newfoundland region. There are undocumented data boring schemes to deal with the unsampled strata. So a lot of the historic catch, and we just had no records on how the catch estimation was done. You can go back to individual assessment documents over time, but I just don't think we're able to recreate the fishery catch compositions anymore. And I think DFO is in the Newfoundland region has looked at doing this a bit, and I think they can only go back to around 96 or something like that. Yeah, I mentioned, so strata are the units that exist every year, and you're supposed to sample all the strata. Gear, quarter, spatial divisions can be regional countries in terms of international fisheries. And clusters are the things that get randomly sampled, like ports, vessels, trips, hulls, etc. And in many areas, the sampling for age is length stratified, and we use age length keys. And even if it's not a length stratified age sampling, you may still be using an age length key to kind of combine the length sampling and age sampling to hopefully improve age composition estimates. And there may be borrowing of age length keys between strata. So complicated information. So then And because the sampling programs are very complex and the statistical properties of the catch size and age comps are, are basically like really difficult to evaluate from first principles. Because I think mostly, well, one big problem is the poorly documented, the sampling schemes are poorly documented and they change over time. So I've never been enthusiastic about trying to do much here. So in my talk, I'm just going to split the thinking based on if composition sample sizes are available or not. Because essentially for a lot of the stocks I work on, the sample sizes are basically not available. I mean, I can ask, but I'm not going to get them. And this could be, there the age sample sizes available, and if because in the East Coast Canadian East Coast context, they're always using lens stratified age samples. So you also need the lens sample sizes available as well. And we may be able to get it for Canadian fleets, but probably it's harder again than to get it for the international fleets that fish off our shores. So fish on stocks outside our 200-mile jurisdictional limit. So first, I'm going to consider approaches that don't require sample sizes.
Hey, Noel, before you go on, just a quick question from the chat. Could you talk about what data inform the estimation of total catch? It seems like it'd be confounded with the state space numbers at age.
You predict total catch using the assessment model numbers or the age via the Baronoff catch equation. And maybe I didn't understand the question. What information?
Well, if you want to go ahead and unmute, you're more than welcome to, or message in the chat, and I'm happy to continue that question.
Can you hear me, Noel?
Yeah.
Yeah, great. So yeah, thanks for taking the question. I guess I've never seen this approach before, so I'm trying to think through how
the censored likelihood.
Correct. Yeah. So
yeah.
I mean, so if you have a bunch of missing catch in your model, I can see how that signal would show up in the data. So the index would go down. There'd be fewer fish for numbers at age. But if you have so is that where it's fundamentally coming from? Is it's changes in the age structure, or if you're missing a lot of catch, you'd essentially truncate the fish ages and then the index would go down?
Index, you're talking about a survey index or something?
Sorry, yeah, like an abundance index or CPE or something.
It's going to try, like with these censored likelihoods, the model will try to come up with the catches that best explain the Z signals, if you will, coming from a survey indices.
Right. And so, yeah, exactly. And so if you have a state space numbers at age, or a state like a time varying natural mortality or something, that would show up in Z as well. So how would the model parse those, or could it? It seems like
so if because this likelihood is flat, so I mean this stock is, well, I will getting into the details of it, but this is a stock where the surveys, I'm not showing that information, but the surveys declined rapidly in the late 80s, early 2000s. Late 80s, early 1990s. And there's just not enough reported catch along with assumed values of natural mortality. There's just not enough of the catch and then not enough Z, if you will, to explain why the stock declined rapidly. So then with these, so that's if you were using the actual landings information. So with this bounds approach, then the model like actually starts putting the catch towards the upper end of the bounds in that period. Now this model, we also have time varying M going on. So because the range of the bounds we put in were still not large enough. Like the upper bounds weren't still not high enough to basically give catches that could explain for the why the stock crashed as it did. So then the model uses M variations to do it, and so it's trading off. Then it's allowed to have time varying M, and it's allowed to have uncertainty in catch, but it's free to put catches where it wants between the bounds, where it's not free to have M deviations that so it'll only have M's varying from. Yeah, it will only have change in M that produces an increase in fit to the assessment information. And that's probably not a very clear explanation.
No, I think it is actually. I think the piece I was missing is that the censored likelihood is flat, and so the model can basically move that around. It's an easier degree of freedom than M, which is constrained by the variance. So that
Exactly right.
yeah, that makes sense. Yeah.
It's free to move catch anywhere within these bounds. So there will be a preference, if you will, to explain lack of fit using catch rather than M. As long, but then you can't have catch go outside the bounds.
Right. So this exactly. Okay, that helps a lot. Thank you.
Okay. Okay. So we were here talking about all this stuff. Yeah. So the bifurcation or the split, if you will. So first, I'm going to consider cases where we don't have information on the sample sizes for lengths and ages that went into producing the age comps of the catch. Primarily, I'm thinking, I mean, that information would be available, would be more readily available from surveys. So likelihoods for catch age proportions. So Chris Francis argued that the multinomial, Dirichlet multinomial distributions are not proper for this type of proportion compositions. And I would argue these distributions just have the wrong correlation structure as well. So Francis concluded that the logistic, what he called the logistic normal, and what I call, because in practice we assume it's logistic multivariate normal. So the logistic multivariate normal distribution shows. And this is an option in WAM. That's the Woods Hole assessment model. But to my knowledge, I'm not very knowledgeable about stock synthesis, hardly, not at all really. But as far as I understand, this is not an option in stock synthesis, but I could be wrong on that. So I'm just kind of interested then about what this logistic multivariate normal distribution is about. Now, there's another one out there too that, like in our assessments or my assessments, I think on the east coast of Canada, we tend to use a different one called the multiplicative logistic transformation. So a leader in the statistical analysis or developing statistical theory for composition data is this guy Atkinson or Atkinson, I think to pronounce it. And he has a book on this business. So he referred to this logistic normal distribution that Francis talked about. He called that the additive logistic. Well, it's based on the additive logistic transformation. And Atkinson argued that for ordered compositional data, such as for ages and lengths, there was another one called the multiplicative logistic transformation. And he felt that was more appropriate to use for that type of data. So in the categorical data analysis world, this multiplicative logistic transformation is also known as the continuation ratio logit. And like you see that discussed in categorical data analysis books like this one by Agresti. It's the one I put because that's the one we used when I was an undergraduate. So it's been this thing's been around for a long time. And this in fisheries world, the CRL has been used for modeling length and age comps by these are mostly the Danish researchers. I don't know this guy, but Rindorf and Peter Louis, and then Casper Berg and Casper Christensen. And there's probably been other people using them. Like it's used also in diet compositions by I think it's Connie Stewart and Chris Field, etc. So the CRLs have been around. Okay, so the additive. So I got a bit sidetracked by the multivariate thing. So what is the additive logistic transformation? So we just let PB be the proportion of catch in bin B. So it could be 1 centimeter length bins or an age bin or 3 centimeter length bins, whatever, some bin. And I just give here's another book on analyzing compositional data. Anyway, there are several books out there on that. So the multivariate additive logistic transformation is just be simple. You take the proportion in a bin, divide by the proportion in the last bin, and take the log of it. And you do that for so basically there's a dimension reduction of 1 for the proportion data, right? Because there's that sum to 1 constraint. So if you have information on big B bins, well, you really only have B minus 1 kind of independent, not even independent, but B minus 1 pieces of information that don't have a hard constraint on them. So that is the transformation to go from proportions to the transform proportions, and the backwards transformation is here. So then basically the additive logistic multivariate normal distribution is just simply based on assuming that these transform proportions have a multivariate normal distribution with some correlation structure. So the multiplicative the transformation is different, but then in the end you transform the proportions and again assume it has a multivariate normal distribution. So the multiplicative transformation is based on these kind of high probabilities, the probability that the state is equal to B given the state is greater than B. Maybe that's how they talk about states a bit vague. But so that's how you do it. And then the transformation then is the log of pi b over 1 minus pi b. And the backwards transformation is here. So this looks complicated, and I guess in some sense it is complicated. So what I've been doing, so in this talk, I'm just going to demonstrate some of the statistical properties of the additive and the multiplicative logistic transformation of simple settings. So the first, I just examine just the simplest kind of compositional distribution I can think of is the Dirichlet. So basically, I just generated a large number of samples from a Dirichlet distribution with proportions P1. Now I'm using A. I guess idea was this was age bins, and then lambda kind of determines the precision or the dispersion of the samples. So these y-i's are like proportions, right? With the Dirichlet distribution, they sum to one. The expected value of the random variables is pi, and then the variance is like this form. So it's a bit kind of like, you might be familiar with binomial or binary variation. So the variance of y is p times 1 minus p, but then you've got this lambda parameter that controls the over dispersion of the data. So there it is. And the covariance then is always negative, right? So because of, and the idea there is because of this some constraint, the covariance between the random variables for any two different bins should be negative, because like if the value is high in one bin, then it should be lower in other bins because the sum has to be one. So that's why you always get this negative covariance and negative correlations between responses with these types of distributions. So anyway, I applied the two transformations to a large number of random simulations from a Dirichlet proportion to investigate what happens with the property. So here's the case one. So the report. So I just imagine that the compositions are coming from this type of structure here. So here's actually the proportions in percent. So category 1, 35%, so on, and down to, I think there's 10 categories. So the categories 10, 9, 8 had just 2% each. And I generate 10,000 samples and get a big matrix of Dirichlet samples, and then here's the article for that. Then I just look at the standard deviations across simulations for each age. Yeah, so I'm counting the bin's age, obviously. So I get standard deviations and then the correlations, and all of this is exactly what this let me go up one slide. Exactly what this statistical theory would have predicted, right? You get all negative correlations between bins, and the standard deviations are doing what the theory would tell us. So these are indeed, so the R function, R Dirichlet, is actually producing data that look like the Dirichlet random samples. So then I applied the additive logistic transformation to these random samples and the multiplicative, and then get the SDs and the correlations. So with the additive logistic transformation, I mean, the SDs are not constant, and you get like large correlations between all the bins. With the multiplicative, the SDs depend on age, right? They're actually depending on the proportions, but you get like independent. And there's statistical theory out there that tells us that if you apply the multiplicative logistic transformation to observations that have like Dirichlet type correlation, then you get independence in the transformed proportions. So this looks troubling to handle in a stock assessment model. This looks way easier. So that's case one. So case two, I just introduced like a kind of a small proportion. So I replaced, I think there was a 7 case one. I'm just gonna check. Yeah, I replaced the 7 with a 1. And I increased the lambda. It was 50 before, now I increased it to 100. I can't remember when I did that. But again, like this is just then the distribution, the SD and correlation of the Y's, and it's all as expected. And then with the transformations, still with the multiplicative, we get independence, but some strange kind of things going on with the standard deviations. This rare age class. I'm calling this age. I guess it is age, but so the age 9, the transformation for age 9, which depends on the rear age 10 age class, has a much higher SD than the other age bins. Well, it's kind of more constant here, but in fact, you can show that the SD of the multiplicative the SD of the transformed proportions using the MLT, if you will, is the same as the SD of the transformed proportion using the ALT. So this one, these will always be the same, but then the SDs at other ages are much smaller for the MLT. And you get like really high correlations now going on. And so one, it's actually pretty easy to see. The additive logistic transformation are always dividing by the same random variable. So that's going to induce positive correlations in the transformed proportions, because you're using the proportion in the last bin for in the transformations for all bins. So this is introducing that correlation, and when this gets small, the correlations get larger. So this is why I don't like to use this one. It's just, to me, it's complicated to how to analyze these additive transformations in the stock assessment context. I think Tim was telling me he has the code to do the multiplicative, but he's just never bothered it yet, or he'd want to do simulations of the two approaches and whatever. And case 3 is one where we just have constant proportions in all age classes, and you don't get as high correlations now, but they're still high. And yes, the SDs of the multiplicative are lower than the additive, except for the last age thing. So but that was just Dirichlet sampling, which would not be, I don't think composition data, real stock assessment composition data will ever resemble like the Dirichlet distribution. So I have some more realistic composition simulations coming from kind of a Dirichlet normal mixture model, AR1 normal mixture model. And the mixture model is straightforward, right? So you get your Dirichlet samples. Then I generate these kind of what I call a gamma matrix. It's just all of this code is just, this red code is just the simulation code for normal AR1 type autoregressive like lag 1 correlation normal distribution, and then you exponentiate it, and then just mix the Y's with this gamma matrix. So you get compositions, but they're just a mixture of Dirichlet and kind of AR1. Probably we should call this like a AR1 log normal model or something. So back to this case 1 again. There's the proportions are the compositions are proportional to these values here. So here is the Y, and so now here's the mixed Y, if you will, the Dirichlet AR1 mixture distribution. And the thing is now it's just a way of introducing positive correlations amongst the adjacent age bins. Because probably in in reality, I mean, this is probably how our data would be looking if we were able to kind of resample or investigate the statistical distributions of our age sampling program. So, then apply the transformations, and it looks this way, still get all these high correlations. What I was really interested here was to see if after this transformation, if these would look to have a kind of a simple distribution. And the answer is not really. This might look to be something like AR1 correlation, but the lag1 correlation depends on the ages. So this still seems to be, a bit difficult to not impossible, but you have to be using something more sophisticated than an AR1 multivariate normal distribution to account for these correlations. And then that one with the rare proportion, again, this is just the raw data. Excuse me. And here's the results. And now you can see that it's really not looking like AR1 type of having an AR1 distribution. This is, I don't know what this looks like, very complicated. And that's case 2. And this is that one with the constant proportion. And, again, still looking, both approaches look a bit complicated. So in practice, we've been using this, and with maybe sometimes assuming independence, which really doesn't look right for this type of sampling scheme, this Dirichlet Aeron mixture distribution, or we might just use some type of simple covariance structure, correlation structure. But this is indicating that the situation may be more complicated. So conclusions for these two distributions. The additive logistic multivariate normal seems problematic because of the dense and complex correlation structures in the transform proportion. We would need to account for this somehow in an observation equation for a stock assessment model and a state-space stock assessment model. And this seems messy. The other thing I probably didn't mention, but might be a bit obvious to some, is this transformation is not unique. I mean, I was dividing by the proportions in the last bin, but you could have used the first bin or any bin really to define the transformation. And I have tried that before using standardizing to different bins, and you get different results. So I use the multiplicative one that is uniquely defined, but there's still problems with it. And a problem for some East Coast assessments that for stocks that have changed in size dramatically over time and have had and have zeros in the composition information is that neither of these distributions support zeros. And I think that is a problem for stocks where the zeros in your compositions are informative. Like for Northern Cod, if you were to plot the composition information as like a kind of age by year matrix, then when that stock collapsed in the early 1990s, there's a V pattern of zeros in the compositions that is highly informative. I mean, you just can't ignore the zeros like we sometimes do in stock assessment models. You get kind of silly results if you do. So that's a problem. And yeah, that's in the surveys for that. That's in the survey age compositions for northern cod. There's not as many zeros in the catch age composition. So, and I can't remember. I think they replaced the zeros with half the minimum value or something like that in the catch age composition, which is a subjective choice, which should be examined. But yeah, I think that's what they're doing. They don't use this compositional likely for the surveys in northern cod, but they in the northern cod assessment, but they do use it for the catch age comps. Okay, the other side of the bifurcation. Oh, it seems like Cole has his hand raised.
Yeah, is that okay to jump in and ask questions?
Sure.
Yeah, can you go back a slide?
Yeah.
Thank you. So yeah, I'm thinking about this third bullet point where it's not unique, and that's a statement about the additive version.
Yes, that's the additive. The multiplicative is a uniquely defined transformation.
It doesn't seem that way though. It seems like you're not conditioning on a specific bin, but if you change the order that you
Yeah. Okay.
combination.
The multiplicative is uniquely defined if if the bins are ordered. It's not uniquely defined if the bins don't have a kind of unique ordering. But for age and length compositions, I think we can define a unique ordering of the bins.
Well, I think you can define an intuitive or natural ordering, like age goes up, but it does seem like if you, for instance, reverse the ages and conditioned starting from the largest age to the lower, you'd get a different correlation structure, and it looks like you'd get a different standard deviation too. And
Yeah, if you yes, if you reverse the ordering or change the ordering somehow, even with the multiplicative, you would get get different results.
so I guess my question is now that I know that's true, does that matter for the stock assessment? Because you essentially could pick an ordering that would have the smallest, say, standard deviation for the ages you cared the most about. Do I have that? I mean, I'm not saying to do that in practice, but just to think through what the implications would be. Because, like, if you reverse the order, maybe you would put more weight on certain ages than other ages. And is that something that you've thought about, or is that worth thinking about?
No, I haven't thought about it. I think I think that if you were to, I mean, really, there would only be so it's either ascending or descending. Uh, well, I guess you could just order them, however, any which way, but the idea with the correlation structure is that we like to think that there's adjacent bins, like that a 6-year-old, like what you get for a 6-year-old should be more similar to 5s and 7s than it should be for 12s or 14s and that. So it wouldn't really make sense to just kind of change the ordering like randomly somehow. Uh, but it would, whether you do this ascending or descending, uh, uh, yeah, probably would make a difference. I've never tried it. I think it probably would. And yeah, you might get different results, and that would be something to think about. Definitely for the additive transformation. I mean, there's where did I have that equation? There's no good reason why you're dividing by the proportion in the last bin. It can be any bin, and I have tried that standardizing to a different proportion. It makes a difference. I don't know which bin would be. Yeah, I guess probably it would be better to standardize to a bin that you have more confidence in the estimation for, um, like a well sampled or a common age. I'm not really sure, and I'm just kind of speculating now, but
Yeah, thanks. I was just kind of thinking that through. Thanks for speculating. I'd be curious to try the multiplicative one where you reverse the order and then put them both in the assessment to see how sensitive it is.
Right. Yeah. Yeah. Next time I play around with this, I could do that. Okay, so now I'm on the second path, the second split. When we have some information on counts, like yeah, I think from most stocks we may have the sense that the uh, we may have some information on the length and age sample sizes, and these may have changed substantially over time, which cause us to want to weight the information differently somehow. I do a lot of assessment. Well, most of the stocks I work on now are moratorium stocks. They're basically bycatch stocks, and that may have had targeted fisheries historically. And the sampling protocols then tend to be quite different for bycatch stocks and targeted species by Fisheries and Oceans Canada. A problem with these moratorium stocks, there can be many zeros, especially in the length comps. And I'll just say lately, just I've been aggregating data to deal with zeros, and I just don't know if it's a good idea. Seems it works in some sense, but I've not specifically investigated the if this is kind of like a cheat, I guess. I've not specifically investigated if it's a good thing or not. And some of the stocks I've been dealing with, I mean, they're bycatch stocks, and they may have only a few, and there's no age sampling, and there may only be a few sets or a few observer sets, if you will, where they take lens samples, and this information has not been expanded for the whole fleet or the whole fishery. So in essence, then my current situation is that I'm working on assessments where we really only have survey catch at length and landings, and we don't have any. Not that we don't have any information on fishery catch at length, but just it hasn't been worked up. The assessment people aren't providing it, so it's not available. The assessment, like the data people, they want to kind of estimate the catch at length for whole fleets, and I think there's lots of things we can do if we have just the individual samples, but they don't really have access to those. So so I have been thinking anyway about how we could use just this sporadic length comp samples that aren't really representative of the whole fleet. And no, well, for sure, I think the multinomial, Dirichlet multinomial are not good choices for modeling fishery age and length comps. These distributions are for nominal categorical count data where the categories have no natural ordering, like A, B, C, D, or red, green, blue, yellow, when you can just mix the orders up and it really shouldn't matter. I think the multinomial and Dirichlet multinomial have wrong covariance structures for fishery and survey comps. And then it seems to be like people use these distributions, well, more than multinomial, and they end up doing kind of more ad hoc or arcane adjustments to, like, a problem when you use these distributions with wrong covariance structures. I find the kind of state-space models and assessment models tend to end up overfitting the composition data because the likelihoods based on the multinomial anyway tend to be to produce large NLLs that the models can only kind of reduce by overfitting the data. And then people use kind of various adjustments to downweight the likelihoods and that. And just to me, it seems like ad hoc and difficult to explain to people. So the fishery comps are like ordinal or even interval categorical count data where the yeah, we can think of like the difference between a 2-year-old and a 3-year-old may be similar to the difference between an 8-year-old and 9-year-old. So that's kind of interval category, kind of using the interval sense of the data, and ordinal is just more like, okay, there's an ordering, but the difference between a 2 and a 3 could be different than the difference between an 8 and a 9, so on. So we expect positive correlations for the thing with this ordinal or interval categorical count data is that usually we expect positive correlations for adjacent bins, and just a more general thing with the complicated sampling designs like highly stratified multi-stage cluster sampling is that we expect high over dispersion in the data. We expect a lot of variability in the counts we get. Yeah, and I've said this already. When we use these distributions, and I don't have a lot of experience using it. I tried them a couple of times in doing assessments, and my sense was that the models were wanting to overfit the comps, so I just went with using something that made more sense to me. So, what will be a good likelihood for catch at age counts? So here's a very oversimplified basis. So we assume somehow that so this I've kind of developed this thinking about if we were sampling a fishery in a particular year, but we could extend this to also to think about how we could include sampling over multiple years. But I'm kind of thinking about this as just sampling one fleet in 1 year. So assume that the sample age frequencies, that we have basically multiple samples from a particular fleet. So that could be just multiple sets or locations or whatever. But this could be year as well. And that the size of the ice sample is xi plus. So the counts are for the ice sample is x1 to xa. I guess I'm thinking about age sampling here, but this could be length as well. So that's the total. So now if these samples were IID Poisson distributed with proportions PA and a lambda I parameter is really just defining the scale of the samples, like whether we're in tens or hundreds or whatever, then most statisticians will agree that the relevant distribution for inferences about the proportions is based on the conditional distribution of the counts given the total. And that conditional distribution is multinomial with those probabilities, and then the total size is xi. And although the counts have this distribution that depend on the proportions and the lambdas, the conditional distribution doesn't depend on the lambdas. So these would be nuisance parameters. What we talk about statistics is nuisance parameters if we're really interested in inference about the compositions, the proportions. So that's nice. But why I call this like a oversimplified basis, because the Poisson assumption will usually not be appropriate. So for various reasons, the composition won't be IID Poisson. They won't be IID and they won't be Poisson. And they won't be both IID and Poisson. The length of age distribution in each sample will probably not be exactly the same because some areas you get kind of maybe smaller fish, some areas you might get like larger fish and so on. So these the proportions will kind of vary somewhat from sample to sample. So a little more realistic basis, and I emphasize a little more realistic, is if we, assume IID Poisson. I didn't have the IID there, but It should be. But so it's also Poisson, but we include some of this kind of a mixture distribution. And the gamma IAs are IID, independent and then identically distributed gamma random variables with mean one and some variance. So this ends up being like multiplicative error terms, multiplicative random effects with mean one. They're just kind of adding a bit of noise to the count. So you can show that the marginal distribution of the xi then is negative binomial, and with mean mu and the over dispersion parameter k such that the expected value of the count is what we want, lambda I PA, and the variance is this quadratic function, and it depends on the k. So Poisson, if k was infinity, this would just be the Poisson situation, right? The variance of the Poisson distribution is its mean. Unfortunately, the separation of information of proportions in the conditional distribution and the lambda I in the distribution of the total no longer occurs for negative binomial counts, even if they're independent. So you don't get like this is not multinomial and so on when it's negative binomial. The distribution of the conditional distribution still depends on the lambda i's and the k, as well as the proportions. So the conditional distribution of the marginal is difficult. Like, it's a complicated distribution. And the gist of it is that the naive estimates of the proportions, right? Just the count in the ice sample, the count in bin A divided by the total is no longer an unbiased estimate of PA. It's not marginally unbiased, and it's not conditionally unbiased either. I mean, it's easy to see it with the conditional distribution because the conditional relative bias is just the gamma IAs, that the multiplicative error terms. The marginal bias is complicated and depends on k and the difference between the total and lambda. I'm not going to get into the details of it, but what I will say is that the negative binomial over dispersion kind of introduces something like covariate measurement error. So there's bias attenuation of the sample proportions. So when I'm talking about the sample proportions are just the counts in the sample divided by the total. There's bias attenuation towards 1 over A, regardless of the values of the proportions. So bias attenuation is like it kind of biased towards the mean. I think it's a good way to think about it. So if the true proportions are like that, then you'll end up overestimating small proportions and underestimating large proportions. And large sample sizes do not remove this bias. So that's the marginal bias. So that's a bit troubling. So that was the slightly more realistic basis. Now I'm going to move on to a better than slightly more realistic basis, which I might call just a more realistic basis. And again, having the same kind of Poisson mixture model. And note that if you take the log of mu, then it's just the log lambda plus log p plus this log gamma term. And this gamma term, this had mean 1, so that the log of the mean of 1 is 0. And so it's kind of in on log scale, this is acting like an additive error term. And the log gamma distribution is kind of similar to a normal distribution. So we can think anyway, with this log link, that these are just additive error terms. So the more realistic basis then is not to assume these were IID, but to assume that the log of the gammas has a multivariate normal distribution with some correlation structure. If we think the errors in the counts for the various bins will be correlated somehow, autocorrelated somehow. And this then defines a log Gaussian Cox process. So it's a conditional on the random variables. You have a Poisson distribution, and the log of the random variables have a Gaussian distribution. So that's the log Gaussian Cox process. Now, one thing we've been looking at, and we've published it, I'm not sure. I think we have a paper in press on it. But it's like a lot of my papers, it's been festering for some reason with co-authors. So anyway, with this log Gaussian Cox process, we can think of if we condition on the random effects, then we can easily show that the conditional distribution of the counts, given the total, and the values for all the random effects and the fixed effect parameters, that just has a multinomial distribution. And the probabilities, if you will, the p's of the multinomial, they change from sample to sample, and they depend on the random effects. And that's the definition of the PIAs here. So it's basically like the population proportions at age, but they're bent or warped or somehow by the random effects, which are again exponents of kind of a log, I guess, AR1, not log normal, but log AR1 multivariate normal distributed. Right? Yeah, here we had. Well, whatever correlation structure. Normally I'd be thinking AR1, but it could be whatever you want. So that's fine. So this approach is then the first condition on the total and the random effects, and then we could get the marginal distribution of this conditional by integrating out the random effects. So we can actually use that as an observation equation. So this is what I call a conditional log Gaussian Cox process, or another name is an approximately conditional NB distribution. So conditional Poisson of multivariate norm is multinomial, and this conditional NB is whatever it's this NBC distribution. It's technically wrong, but a useful approach, I think. You should really get the marginal distribution, then condition. That's the right way to do it, but it ends up you get a very complicated distribution. You don't get the separation of information about lambdas and p's. Whereas in this approach, you do get that separation of information. There's no lambdas in this distribution. And then when you integrate out the gammas, there's still no lambdas in this distribution. So we've been looking at that one. So this conditional log Gaussian Cox process is different from the multinomial and Dirichlet multinomial, both in variance and correlation structures. And the conditional log Gaussian Cox process doesn't have all negative correlations like multinomial. So I think I have some, again, just simulate some data that illustrate this. So the comps are coming from the case 1 scenario. And I'm thinking if NS sampling events. So NS is 20. So it could be years, could be number of ports or something like that. And the over dispersion is coming with the what I call sigma p. So that's the sigma of that AR1 process is 0.5, and correlation set to 0. So again, we had this gamma matrix. That's kind of looked at this before, and we get these mixed values of the proportions. So that's what this part of code is doing. And then once you get these mixed proportions, then you just your data generator is multinomial with the random proportions, if you will, for every sampling event. And then we can get the observed proportions. Yeah, just straightforward. So here's this case one data generator. So just giving a little bubble plot of this is the log gammas, I'm counting them, right? They're just a IID normal in this case, because I set AR1 the autocorrelation parameter to be 0. So somehow then you use these gamma, right? You exponentiate these things and mix up your population proportion to get these. So the population proportion here is the black line. The randomized proportions are these colored lines, right? So there's a different colored line for every sample. And then the sampling is multinomial given the randomized proportions, if you will, or mixed up proportions. So then you get your composition samples, and this then is just the observed proportions, right? The count in the H bin divided by the total. So that's the gist of the how the sampling works. So then this is a bit of TMB code to fit this type of model. It's pretty straightforward. You just get the distribution of the counts conditional on the random effects is multinomial, and then the distribution of the random effects is just AR1 for each sample. So then I do this 1,000 times and look at the distribution of so we can estimate the population proportions either using just the straightforward counts, or we could use actually the negative binomial, the conditional negative binomial estimator different. And so here is just the root mean square errors of the estimates of the population proportion. So what I'm talking about now, you can actually estimate the black line given the 20 samples and so on. This is a simulation, so I know the true values of the population proportion. So anyway, here's the root mean square errors, and here is the correlation of the deviations between the estimates of the population proportions and their true values. So but what's interesting to me is that the correlation in the estimates of the population proportions is not like the multinomial or Dirichlet multinomial. It's not too different, but you get some positive correlations even when the correlation in the mixing variable was 0. So just the Poisson over dispersion can do that, which that was a bit interesting. And simulation summaries. So the black line here is the truth, and so now we could estimate the population proportions using this conditional MB distribution, or assuming they were multinomial, and they're pretty similar results either way. There is that little bit of bias in the multinomial, and this is that bias attenuation I mentioned earlier. So you tend to so just keep in mind what the proportions look like. What I have them too. The first bin is has a P of 0.35, and it goes down. The last bins have P's of around 0.02. So you tend to underestimate the large proportions and overestimate the small proportions if you assume the counts at a multinomial distribution. The MBAC corrects it well. That's not surprising. I'm using the right data generating. I'm using the same likelihood for estimation as the data generating distribution. So, and you get a little bit higher root mean square error for the multinomials. But not multinomials not behaving too bad. but you're not getting the right correlation structure. And this is just then comparing the SDs of the multinomial type estimators of the population proportions with those of this conditional MB, and yeah, things look pretty similar. Correlations and that. So even though you use the wrong distribution, like your estimates still don't beat structure that the multinomial assumes. And from a stock assessment context, this is something I don't like. I mean, this would be the values of the NLLs based on the optimized fitted values, and so the multinomial tends to be a lot higher than a lot higher than the negative binomial. So then in a stock assessment context, if you were assuming multinomial, then the models would want to be trying to reduce this relative to other data sources, and it doesn't have quite that same issue with using this conditional approach. Yeah. So then, like just a second case. So now we have again the same proportions, but I'm just looking at, so the first case with 10 samples, 50 per sample. This one is 10 different samples, 100 per sample. And I'm including some correlation now in the mixing distribution. So these aren't ID normal, these are like multivariate normal now with lag 1 autocorrelation of 0.5. So you tend to get like for each sample, you tend to get like some patterns in the in the mixing variables. And you get the basic gist of this is that autocorrelation then is kind of inducing more autocorrelation in the estimates of the proportion. So if we were given these estimates, even if they were developed assuming that the data had a multinomial distribution, but if we were given a series of these estimates and wanted to kind of include the information in an assessment somehow, we'd want to be doing it with accounting for this type of correlation structure somehow. Although it's a complicated correlation structure. Same basic thing going on here with the different counts. Probably not as much difference in the multinomial NLL compared to the negative binomial. When I did this first, maybe about 10 years ago, I was getting huge differences. Now I'm thinking on it, maybe it's because I need to have more sampling events. Maybe I need to have like 50 sampling events. I couldn't remember how I got such big differences, but because I redid these simulations recently, maybe that's what it is. Case 3, 10H samples. But so the only point I'm making here is if we have high autocorrelation in the mixing distribution, that actually doesn't often autocorrelation, like statisticians talk about how it boosts variability, but it doesn't boost variability in this type of mixture distribution, because when the autocorrelation in the mixture distribution is high, then it actually doesn't have much effect on the proportions. And do I have that? And that's because of how the random proportions are generated. Like if these gammas don't depend on age, then they don't do anything. They just cancel in the numerator and not the denominator. That's why with the high correlation, I actually didn't get very high correlation in the random proportions, these PIAs. And then basically the data are generated multinomial PIA. And because, so those PIAs all look more similar. Still, we ended up getting some positive correlation in the estimates. So I'm just comparing it. Then this is Now this is not multinomial. This is comparing the MB estimates of the conditional MB estimates of the population proportions when the autocorrelation was 0.9 and compared to 0.5. And yeah, I think the correlations are a little bit less here. Not always, but maybe not that much actually. And you still get that. Yeah, I think that like the bias is a bit larger, it's a bit smaller. The multinomial bias is a bit smaller when the autocorrelation is high compared to when the is around 0.5. And the root mean difference in root mean square errors is a bit less. So it's a kind of a strange situation where high autocorrelation doesn't have the same boosting effect that it might in other situations. Okay, so I'm starting to finish up now. So now I'm going to switch to improved realism. So I'm going to actually generate survey data using the sim survey package. So that has been published by Paul Regler et al. In the PLOS One journal. And my simulations I'm using, so there's a paper that kind of did some simulations of surveys and was published in the ICES journal recently, 2023. So I'm using just exactly their cloud-like population simulation scenario. So a bit on sim survey, it basically simulates an age structure population over time. You fix the ZADs and other things, and it distributes the numbers at age throughout over a spatial domain using some type of random effects and there's spatial correlation in how the population is distributed over space. And I think there may be some also age correlation too, and there's time series correlation and how it evolves over time. I mean, I can't remember the details of the sim survey, but the papers are there. So then basically, it distributes the population over space, and then it runs a stratified random survey and sampling like Fisheries Notions Canada do it. So I did 500 simulations of just one population. I mean, it's easy to change the population, and ran the survey, and then here I'm just looking at length composition results. So, and I ran the population for 20 years, and this is showing the red line is the true proportionate length in the population, and the vertical bar, these are box plots of some type, and they're indicating the simulation results of the design-based strata area weighted average estimates of the survey mean numbers per total at land, and then we just divide by total to get the compositions. So anyway, the surveys are tracking the true comps pretty well, and it's kind of a bit hard to see what's going on here. So basically, I just do box plots of mean length from the survey, and then the red line is the population mean. So kind of tracking it okay. And the simulation results, then the bias of the compositions. I'm not really sure there's this, I guess, at the very small lengths, so there's logistic type length selectivity going on in the survey. So at very small lengths, the survey just doesn't catch the sizes. So then you get this minus 100% negative bias, right? Because the observed is 0 and predicted is small, but then you divide. This is percent bias. So anyway, you end up getting 100% bias. But when I look at the percent bias, so for large fish and small fish, so for the larger fish greater than 50 centimeters, you see it tends to be, so the way the distribution is, the larger sizes are have smaller proportions, right, or more rare. And so we do have this kind of bias attenuation for the larger sizes. So and this is, oh, right. This is, I think that might be blocking the view. So when I'm plotting the bias for each year versus the true proportion at length. So these are so this would be basically the largest sizes with the small true proportion. So then you're overestimating the small proportions, and then the bias goes pretty much zero for the larger proportions. So it's not exactly like the bias attenuation situation I outlined earlier, but there is some of that going on. But then at small sizes, it's weird. I don't fully understand what's going on there. And then we look at the distribution of the compositions. So here's just basically it's probably the root mean square error versus length. But really, I was interested in this correlation structure, and I've just done the correlation structure for 6 years. So that's each panel is a year. And I mean, you can see this clearly not like multinomial, like radically different than multinomial type. So it seems what's going on is like if you basically overestimate if you overestimate the proportion in the small bin, then you'll tend to overestimate proportions in neighboring small bins, but then of course you underestimate the proportions in larger bins, so you get this kind of like seesaw effect. And so those were the results there. Overall conclusions. Oh, for some reason animation got turned on. So overall conclusions. So first bullet, I think this is dealing with uncertainty total catches. So we'd like to do that in stock assessment, but in practice, this uncertainty may be poorly understood, and then that makes it difficult to include in an objective way anyway in a stock assessment model. I think my other overall main conclusion is that the multinomial and Dirichlet multinomial are for distributions are for a different type of data than length and age comp samples are. We need more realistic models for the statistical distribution of age and size comps. And there's, several have been proposed in the literature, maybe more than several. So the additive logistic multivariate normal, I think that has difficult statistical properties. I've been using the multiplicative one, although that has issues as well. And although I'm not reporting on that, I was also applying that when this log Gaussian Cox process type of counts, and didn't seem to work very well. This conditional log Gaussian Cox process is a flexible composition model, but I mean that's one where you actually know the counts, whereas up there we're just assuming we only know the proportions, and all of this stuff needs testing within stock assessment model frameworks. But I'd like to just do the testing on some simple frameworks first, like the simulation procedures I've outlined here, to get some kind of intuitive understanding of what's going on. But really, these should be tested in stock assessment model frameworks as well. Yeah, it's also good to have, when doing it is before you start putting something in a stock assessment model, it's good to have some kind of basic understanding of what the sampling properties of your data are. Okay, so that's it. That's just like a leftover slide. That's all I have to present.
Okay, perfect. Thank you, Noel. That was a awesome presentation. I'll now open it up to everyone else for questions. Feel free to go ahead and just unmute yourself and ask Noel if you have any burning questions. Okay, looks like we don't have any. Oh, Cole, go ahead.
Well, nobody else is jumping in, so I will again. Yeah, thanks, Noel. This is maybe a crazy thought, but you know, you had me thinking about the correlation of the data more than I ever have, or composition data before. Is there some way that we could, I don't think we look at that enough, maybe. Is there some way to formalize a test where we could look at the correlation of the, count, sorry, like our age composition data and try to like infer whether the multinomial would be reasonable or unreasonable? Kind of like looking at this slide in the bottom left, like if there's some way that we could
Yeah,
transform
well,
our data
that
and like have a exploration before we model, make an assumption in our assessment. Did that question make sense?
yeah, and like all this is the observed proportion minus the true population proportion, but in a stock assessment model will be the the proportions you're getting, say, from the model predicted proportions, and you just so you get those every year, and then this is just the correlation of those deviations over time. I think that's all this is.
Yeah, so you could just have a plot that compares that to the like if you're using a multinomial, you could calculate the correlation analytically and compare them. Would that be a reasonable diagnostic to do?
Hmm. Yeah, well, I don't know. Maybe not. Maybe you'd want to do like maybe maybe you'd want to look at the correlations in one of those like the multiplicative logistic transformation or something, because you might expect that to have a more continuous distribution. But the problem is if you have like the uh, uh, if your compositions have zeros, then that won't be defined. But I think for but if your compositions have zero, yeah. So if you have a lot of zeros in your compositions, that'd be a problem. But if you don't have a lot of zeros, or if you like use plus groups or whatever, when you start seeing a lot of zeros, then I think I would prefer that. I think the that diagnostic test might be better based on the 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 multiplicative logistic transformation. So you just transform your compositions and transform your model predictions, and then look at the correlation structure and those things. I'd probably do it both ways. Uh, so if it was multinomial type correlation, hopefully the with that the multiplicative logistic transformation, you should end up getting like basically no correlation. But if you just do it under proportions, then you should get something more like the Dirichlet results. Like, so if I go back to the Dirichlet stuff, that is just that's the mixed stuff. So this is just looking at when I do the correlation of Y. So that's the Y's are just the Dirichlet samples. Uh, and they're just like proportions, right? And all I'm doing here, I'm just looking at uh, the correlation. This may just be the correlation of Y. Really, it should be the kind of expected value of Y minus the model Y.
Right, because
Here it
here
just may be.
the underlying population is the same, but we have big changes in age structure over time, so we don't have like clean replicates. But if you do it against the expectation, it seems like it would work.
Yeah, so like for that's the case um in that sim survey example. So this was, yeah, these correlations are just looking at the let's just get the deviations from the estimated length, proportionate length, minus the true proportionate length, not the average overall simulations, because there's a bit of bias going on, but it's actually the population values. And in a stock assessment context, this would be the stock assessment values. And then you just look at the covariance of the deviations.
Yeah, that makes a lot of sense to me as an additional diagnostic on top of just like, let's say, residuals or something like that. Yeah, that's really interesting. Thank you.
So some of what's going on here, these positives and negatives are being driven by the bias as well as the correlation. So because this is standardized relative to the truth. If I standardize, took the deviations from the simulation mean, that would not be reflecting this bias business. So, but anyway, that's what you'd want to do in a stock assessment context. Take your observed composition minus the model predicted composition, and then just look at it. And I'm pretty sure you're going to be seeing this well, I don't know, not this bad, but you're going to be seeing some positive correlation across ages for lengths for sure. Maybe for lengths, maybe not quite the same for ages, especially if you don't have that many age bins. But if you have a model with a lot of ages, then I think you should be seeing something like this. Okay, thanks.
Yeah. Any other questions? Okay, in that case, let's go ahead and thank Noel for a wonderful talk, and thank you again, Noel, for a really engaging talk. Really appreciate it. Super interesting stuff. And again, thank you everyone for joining. It was a wonderful quarter, and I'm looking forward to seeing hopefully all you guys next quarter, as we have a whole new slate of wonderful speakers to go ahead and engage more in fisheries research. So thank you again, Noel, and thank you again, everyone, and I hope you have a wonderful rest of your week.
Okay, bye-bye.